Today we're going to talk about automata on infinite, and this is basically an extension of what you've already seen about normal automata. So you've seen deterministic finite automata and non-deterministic finite automata. Probably I'm going to give you a very short refresher of that as well. But what we're interested in are basically automata that work on infinite words. So this is a continuation of what we were doing with the games. So if you remember how our games worked, every play of the game was an infinite path on the game graph, right? So here I want to also have something similar. I want to have an automaton, and then I want the input to this automaton to be an infinite word, okay? But before that, let's just recall the definitions of automata on finite words. So we said, we know, I mean, I hope that you know from your previous courses that a deterministic finite automaton basically has these parts, and it looks kind of like this. So you have an alphabet, which you use to basically write your words. So every element in this alphabet is called a letter. You have a finite set of states. In this case, I have two states, Q0 and Q1. You have an initial state, which I always show it with Q0. So the automaton always starts at this initial state. And then you have a transition function, which basically tells you that if you're in a particular state and read a particular letter of the alphabet, which other state you're going to go to. The way I show it on the graph is just by labels over the edges. So what this means is that if I'm at Q0 and I read the letter 1, I will go to Q1. Okay. And then I also have a set T, and I've named it T because I want you to really see the relationship between this and target vertices in games. So we have a set T, which are the accepting states, and I generally show them in blue. Okay. So the way this works is that I start at the starting vertex at Q0, my initial vertex, and I just read my word letter by letter. And every time that I read a letter, I take the transition corresponding to that letter. So for example, if, let's say my word is 00101, I start here, I read the first 0 and I do the into 0, which keeps me here. Then I read the second 0, do the same transition. Then I read 1 and go here. Then I read 0 and the transition for 0 keeps me here. And then again, I read the last 1, which keeps me in Q1. So for this particular word, I will end up at Q1 if I run my automaton on it. Okay. So now I want to say that this automaton is basically a decider. It either accepts a word or rejects it. And the way I do that is very simple. I say, run the word. If the run on this word ends in an accepting state, then the word is accepted. Otherwise, the word is rejected. Okay. So this gives me basically a set of words that are accepted by this automaton, and we call that the language of the automaton. So the language of this automaton is the set of all the possible words that are accepted by this automaton. So as an example, what is the language of this particular automaton here? So what strings, what words are accepted by this automaton? And remember, our words are finite right now. Yeah, so any word that has 1 in it will be accepted. Because basically what this self loop here does is that it ignores zeros, right? So any number of zeros at the beginning of the word will just be ignored. I will stay in the same state. And then as soon as I read a 1, I will go to the other state. And then as soon as I've come to Q1, it doesn't matter what I read. Again, everything is ignored. And I'm going to end up in Q1 and I'm going to get accepted. So this automaton accepts all words that have at least 1 in them. Okay. Now, of course, what's interesting for us is to extend our definition of automaton to have non-determinism in it. And we've talked about non-determinism in the context of programs before. In the context of automata, it's actually very similar. So very simply, the idea is that let's say I can have more than one starting state. Let's say I can have a set of initial states and I can start from whichever I like. And let's say that my transitions are also non-deterministic. For example, here, from this state Q0, if I'm at this state and I read the letter 1, I have a choice. I can go to Q1 or I can go to Q0 prime. Okay? This is what we call non-determinism in an automata. So if I want to give a more formal definition, the more formal definition is that, again, it's an automaton is something that it's a tuple that consists of all of these things, but it has an alphabet, which is a finite set of letters. It has a finite set of states. Now, the thing that has changed, one thing that has changed is this one. So instead of just having one initial state, I have a set of initial states. And you can see it by these arrows here. So here I'm saying that both Q1 and Q0 are initial states. And then my transition function also changes. So previously, the transition function said, if I know which state I'm in and what letter I'm reading the next state, but here it says that given a state and the letter that you're reading, I'm going to give you a set of states. And you can transition to any of them. Okay? So these are the two parts that have changed. And again, I gave you an example here. If I'm at Q0 and I read the letter 1, I can go to both of these places. Similarly, if I'm at Q1 and I read the letter 0, I can take this transition and remain in Q1, or I can take this one and go to Q0. But now, since we're introducing non-determinism, the result is that for a given word, I don't have a unique run. So in the deterministic case, if I gave you a particular word, you had only one run of the automaton. But here, for any word, you can have many different runs, right? Because you have choices, right? You have a choice of where to start, and you also have a choice of which transitions to take sometimes. So we have to, again, language of the automaton, and we have to say when the automaton accepts a particular word. And this is the classical definition that we use. We say that a word is accepted if there is a run that accepts. So the definition of accepting run is the same as before. A run is accepting if it ends at an accepting state, right? If it ends at one of these blue points. But now I'm saying that for one particular input, for one particular, and have many different runs. So I say this input is accepted if there is at least one of these runs that ends at an accepting state. Okay? Another way of looking at this, another intuition for this would be that our automaton is somehow extremely smart and knows which run to take and always takes the run that accepts, if it can. Okay? But anyway, this is the background that I expected you to have from theory of computation courses, probably. If you haven't seen these things before, just search on YouTube. There are a lot of really nice videos that explain DFA and NFA. What we are actually interested in are automata on infinite words. So I want to see what happens if I have an automaton, and instead of giving it a finite input, I give it an infinite input. Okay. And this is actually also what we call omega automata. And again, if you've passed set theory, this omega is like the smallest infinite ordinal. It's the size of the set of natural numbers. But anyway, whenever I say omega automata, what I mean is that it's an automaton that is taking an infinite input. Okay. So now what happens if I take the same two automata as the previous slide, and I say I want to give you an infinite input? Now for this one, I will still have a unique run because it's well defined where I start, and I have a I have a unique starting point. And then at every step, I have a unique transition that I have to take. Okay. So I get a unique run, but this run is also infinite. It's like an infinite pass on the graph of this automata. And what happens in this case is that I can actually have many different runs. And this was the case before as well. I could have many different runs on the same input, even when the input was finite. But now that the input is infinite, I can potentially have infinitely many different runs right? Because imagine that my word somehow gets to this point infinitely many times, and each time I have a choice of which transition to take. So it's possible that I have an automaton and a particular infinite word, and when I feed this infinite word to my automaton, I have infinitely many different runs. And of course, every run itself is infinite. But fine, we don't really have a problem with having many runs because we can use the same solution as before. So before I said that a word is accepted if there is a run over that word that is accepted. So here I can use the same technique. I can say if I have many different runs or even infinitely many different runs on some particular word W prime, I say that W prime is accepted by my automaton if there is at least one of the runs that is an accepting run. But now the problem is, how do you define an accepting run? That's a much more problematic situation, right? Because before we said that every run ends up at a particular vertex. And then we said that this run is accepting if it ends at an accepting state. But now I have infinite runs. My runs never terminate. So I don't have a last state. I cannot say I accept only if I end up at a particular place, because I don't end up anywhere. So what can I do? I can basically have the same definitions as before. These are the same definitions. It's just that the input is infinite. So I have a deterministic automaton and a non-deterministic automaton. But I'm just going to say that I'm going to have an acceptance condition. And the role of this acceptance condition is to tell me whether a particular run is an accepting run or not. And as we saw, I cannot just say, look at the last vertex, because there is no last vertex. Now, one of the first things that come to mind is, let's use reachability. Let's say that my run is an accepting run if it reaches one of the accepting states. Okay, but it turns out that's not very expressive. If we use reachability as our acceptance condition, there are very few different languages that we can actually model with our automaton. So it's not really interesting. And if you think about it, that makes sense, because reachability is, in a sense, a finite property, right? But we want to talk about infinite runs. So intuitively, it's better if we can use something like Büchi or parity. Okay? So I can use the Büchi condition, for example, and I can say, okay, in my automaton, I'm going to have some set of states. I'm calling them target states or accepting states or whatever. These are like the blue states. And I say that a particular run is accepting if it visits the blue states infinitely many times. Okay, that would be Büchi. Let me see if I have a slide for it. Yes. Okay. So in the Büchi automaton, I just say that I have a set T of accepting states and then a run, accepting run, if it visits T infinitely many times. So if the set of vertices that are seen infinitely many times in this run intersects T. Okay. And again, if I have a non-deterministic automaton, I say that a word, an infinite word, is accepted by the automaton if there is at least one accepting run on that particular word. Okay. Now for parity, I can do something similar. Today, we're not going to talk too much about parity, but I'm just going to define it anyway. So it's just like the game. I'm going to assign a priority to every state of my automaton. And then if I have an infinite run, I can check the parity of the run, which is like the smallest priority that was seen infinitely many times. And I can say this run is accepting if this smallest infinitely seen priority is even. Otherwise, this run is rejected. Okay. So I can have automata with Büchi conditions or with parity conditions, and I can also have deterministic or non-deterministic variants of both of them. Okay. So the notation that we usually use is that we write dBW for deterministic Büchi automaton. They chose W because A was already taken for the finite automaton. So it's deterministic Büchi automaton. I don't know why. And we also write like NBW for non-deterministic Büchi automaton, and then for parity, it's just DPW and NPW. Okay, let's do some examples. So let's say that I'm just working with Büchi automata. So imagine all of these automata are Büchi automata. I want you to tell me what the languages of each of these automata are. So what are the set of infinite strings that each one of these automata accepts? So let's start with this one. What words are accepted by this automata?
All number of one.
Mm-hmm.
Oh, no.
No, so a word is accepted if I see the accepting state infinitely many times.
Infinitely many times.
Because it's a Büchi automaton, right?
Infinite number of one.
An infinite number of ones. Yeah, that's, I think, the correct answer. Let's see. So let's get some intuition. What does this transition here do? It basically says you can ignore a bunch of zeros, right? So you start here, you ignore a bunch of zeros until you read a one and you go here. And then when you read a one and go to the accepting state on the right, no matter what you read afterwards, you're going back here. And then again, you're ignoring zeros until you see another one, and so on. So the only case where you will actually visit here infinitely many times is if your string has infinitely many ones. Because every time that you come to the right state, in the next step, you are pushed back to the left state, and you can come back only if you read a one. Okay. So I proved that if a string is accepted by this automaton, then that string has infinitely many ones. But let's prove the other side. Let's prove that if a string has infinitely many ones, it will be accepted. So if my string has infinitely many ones, I don't care about the zeros. I eventually reach one of these ones and go here. And then I might waste one of my ones going back, but it doesn't matter because I have infinitely many of them. And I can again find the next one and go back right. So this shows that if I have infinitely many ones, it will accept. So this automaton basically accepts all the strings that have infinitely many ones in them. Nice. How about this one? Second one.
Oh, if we reach a target and then we receive zero, we will remain in the target, right?
No. Okay, so whenever we don't have a transition, what that means is that if we read a zero here, we're going to reject. Okay, and the explanation for that is that, like, you can imagine that you have a trap, and if you read a zero, you go to that trap, and you will always remain in that trap. Okay, but I usually don't draw these traps. I just, if you don't have a transition with a zero, it means that if you're here and you read a zero, you reject.
I don't know. I think I should have continuous ones afterward, but I don't know initially.
Yeah, so you're correct, actually. So let's do this. Let me change my color. So I start here. What does this edge do? It just ignores a bunch of zeros and ones. So I can ignore a finite prefix of my string, whatever it is, using this edge. Again, this is just intuition. But then at some point, I have to decide to go to the right. Okay. And by the way, this is a non-deterministic automaton because you can see that with 0 and 1, I can remain here or I can go to the right. But when I decide to go to the right, as soon as I make that decision, I have to only see ones after that. Because after that decision, if I see a 0, I will get rejected. Okay, this is a rejecting state, basically. So this means that my string, my input string should have ones at some point and then everywhere after that point. So there should be a point after which I only have ones. This is like Kobuki. It's like Kobuki of one in a sense. Okay, so yeah, this is basically my assumption. I'm assuming that the set of strings that are accepted here is this. I have a bunch of zeros and ones, but finitely many of them. And this is followed by a 1 for infinitely many times. And this is how I write it as a regular expression. Okay. Now, again, why does this work? So first of all, if I have a string that is accepted here, it means that I had an accepting run. And the only way I can have an accepting run is to go right and then remain there, which means that I had ones at some point and at all times after that point, right? On the other hand, if I give you a string that is like this, that has ones at some point and after that, there is a run that accepts that string. And that's the run that goes to the right just at the right time, just when we're sure that there are going to be only ones afterwards. So it ignores all the zeros here. And then as soon as we run out of zeros, it goes to the right. Okay. Nice. How about this one?
All the number of ones.
What do you mean?
Oh, one say infinite number of ones.
An infinite number of ones. So you say this is the same as the first one?
Oh no, not really. So I think the number of in order to make it infinitely many times, the number of ones appearing should. Oh, how to express that? In order to stay in the target, I know that the number.
Can you speak up? I cannot hear.
If it has finite amount of one, then we will have one number of ones.
Yeah, okay, so let's consider two cases. Either my string has a finite number of ones or an infinite number of ones. If it has an infinite number of ones, it will definitely be accepted, right? Because I can just take these forever, right? But if it has a finite number of ones, it should have an odd number of ones. Because the first time I read a 1, I go to the right. The next time I read a 1, I go back to the left, and so on. So if I have finitely many ones, I have to make sure that I end up on the right so that I stay there forever and then I get accepted. And the only way for that is to have an odd number of ones. This automaton accepts all the strings that either have an odd number of ones or an infinite number of ones. Now, what's really interesting here is that just how expressive we are. Like, this is a very strange kind of language, but we could express it with just two states in our automaton. And we will see later that these automata are extremely expressive. Like, there are so many different properties that you can write as an automata. Okay, how about this one here? What is the set of inputs that are accepted by this automata?
Let's say infinite 1-0 pairs.
Infinite 1-0 pairs. Okay.
1-0 right after 1. Such a pair should exist infinitely many times.
Okay, what you're saying is correct, but can you say it in a simpler way? So what does it mean for a string to have infinitely many 1-0s? It means it has infinitely many ones and infinitely many zeros, right? These two things are the same. Because if you look at your string, you have a bunch of zeros, then a bunch of ones, then a bunch of zeros, and so on. And if you switch from 1 to 0 infinitely many times, that's the same as saying I have infinitely many ones and infinitely many zeros. Okay, so our guess here is that this automaton is going to accept any string that has both infinitely many ones and infinitely many zeros. Why is that? So let's say I have a string that has infinitely many ones and infinitely many zeros. I start here. I take this 0 until I reach a 1, and then I take this 1. And then again, I take this 1 until I reach a 0, and I then take this 1. I reach my target. I take this 1 back, I'm here now, I just continue the same strategy. So I will see the target infinitely many times. But this was assuming that I have infinitely many ones and infinitely many zeros. But now let's say that I have only finitely many ones. So every time that I reach my target, I'm using at least one of these ones, right? And then I'm kicked back to the initial state. So if I have finitely many ones, it's impossible to reach this target infinitely many times. I can say the same thing for zeros. Every time I reach this target, I'm using at least one of my zeros, so I need infinitely many zeros. So yeah, this one accepts the set of all strings that have both infinitely many ones and infinitely many zeros. Okay. How about this one? Is it?
Infinite many ones.
Why do you think it's the same? Because, I mean, it looks different, right? Before if we were here and read a one, we would go back to the left, but now we're.
In this case, if we want to say in the target for infinitely many times, all the in edges going in that target is one.
Yes.
I think it is even simpler than the first one.
Well, I mean, they both have the same number of states, so I don't think it's simpler, but yes, it accepts the same language. That's true. Okay. So the reason I included this is to just show you that for the same language, we can have many different automata, and even we can have different minimal automata. So I have two automata for the same language, and they both have only two states. And I guess it's easy to prove that you cannot have an automaton with one state for this language, right? Because an automaton with one state either accepts everything or rejects everything. Okay, so yeah, automata are not unique. So the same language can have many different automata, and they're not unique even if we say we want a minimal automata. Okay. Now, one theorem that you've probably seen about finite automata is that deterministic and non-deterministic finite automata have the same expressive power. Which means that if you have a language that has a non-deterministic finite automaton, that language also has a deterministic finite automaton. Okay. Now, again, if you want a proof of this, just Google it or search on YouTube. It's a very classical result. You just have to do subset construction, and the DFA is actually going to be much larger than the NFA, but it doesn't matter. What matters is that if you have an NFA, a non-deterministic finite automaton for a language, you also have a DFA. Now, I want to say that this is not the case for Büchi automata. So I want to say that there are languages that can be captured by non-deterministic Büchi automaton, but they cannot be captured by deterministic Büchi automaton. Okay. Let's look at this automaton. It accepts all the words that have finitely many zeros. Or basically all the words that are just one from some point onwards. Right? We saw it here as well. This is the same automaton. So basically what this automaton does is that it ignores some prefix, and then at some point it chooses to go right, and if it goes right, it has to only see one from that point onwards. So it accepts if you have only finitely many zeros. Okay. Now my question is, can you find a deterministic Büchi automaton that accepts the same language? Okay, so this is a non-deterministic automaton because, of course, like if I'm here and I read either 0 and 1, I can either stay or go to the right. So I have non-determinism there. But can I have a deterministic automaton that accepts the same language?
Yes.
Why do you say yes?
Maybe and that zero to stay in the non-target vertex and then one transit to the target vertex.
Mhm.
And then stay in one forever.
Try to draw it and see if it works.
Oh my God, no. Sorry, no.
Okay, so intuitively the answer is no. And it's no because if you look at the runs of this automaton, these runs, the only one that is really an accepting run, or okay, not the only one, but okay, the runs that are accepting here are the runs that know when to go right, right? And they go right only after having seen all the zeros. But in order to be sure that you've seen all the zeros, you have to somehow know something about the future. You have to know that what I've read until this point contained all the zeros, and I'm not going to see any zeros in the future. But you cannot do that in a deterministic automaton, because a deterministic automaton only knows what happened in the past. And it doesn't have the option of branching and saying, oh, maybe I do this or do that. It has to make a deterministic choice based on what has happened in the past. So intuitively, we think the answer is no. But intuition is not good enough for us. Let's say we're mathematicians, we want to prove this. So prove that there is no deterministic Büchi automaton that would accept the same language. Actually, let me give you the proof. So the proof here is actually very similar to what we call pumping lemma for non-deterministic automata. Let me add a slide here and let me just try this. Okay, let's say that I want to have a proof by contradiction. Okay, it's really hard to write by hand here, but it's okay. So let's assume that there is a deterministic Büchi automaton that accepts this language. So what is my language? My language is basically this. It's 0, 1 star followed by 1 omega. So it's the set of all strings that have finitely many zeros. Okay. Set of all strings with finitely many zeros. Okay. Now let's just assume that there is a deterministic Büchi automaton that accepts it. And let me give this language a name. Let's call it L. So assume A is a deterministic Büchi automaton such that the language of A is L. So it accepts exactly these strings. Now, every automaton has a finite number of states, okay? So I'm just going to give it a name. So let n be the number of states in A. And I know that, of course, this is finite. Because remember, when we were defining our automata, the number of states was always finite. What's infinite is the input and the runs and so on. So, but the number of states is finite. Okay. So now I want to consider some words. And the first word I'm going to consider is the word that just has ones. Okay. So consider this word. It's an infinite word and it only has ones. So my automaton A should accept this word. But this is a Büchi automaton, which means that the run on this word had to reach some accepting state, and it had to reach accepting states infinitely many times. Okay, great. Now, the other point I want to make here is that I can really talk about the run on this word instead of a run, because I'm talking about a deterministic automaton. So on every word, I have exactly one run. Okay. So let's say that I take the run on this automaton and I just write the states that I reach at every point. So I start at Q0, then I go to Q1, Q2, so on. At some point, I'm going to reach an accepting state. So let's call that Q I, okay? So Qi is an accepting state. This is the first accepting state that I reached. And I reached this after reading I1s, basically. So now I say, instead of this string, which was 1 all the way, consider the string that is 1 until position I, and then it's a 0 at position I plus 1, and then again 1s after that. This string also has finitely many zeros. It has only 1 0. So this string is also accepted, which means that there is another index somewhere here, let's call it Qi prime, where this entire string has reached to an accepting state, right? Because this string is accepted, it reaches infinitely many accepting states. I just take the first one, I call that Qi prime. And again, remember, whatever I don't write here is just 1s to infinity. Okay, now I can do the same thing. I can say, actually, let me change the names. Instead of I and I prime, let's say this is Qi1 and this is Qi2. Okay, so I do the same thing. I know that if I start from here and I run this string, I will reach an accepting state here. So I do the same thing. Let's copy this. But then instead of just putting 1s after this, I put a 0 and then I put all 1s. Again, this third string has to be accepted. So this third string has to reach an accepting state after Qi2 because it has to reach infinitely many accepting states. So I take the first accepting state and I call that Qi3. And I just continue this. I again create another string that is the same as the previous one, except that it has a 0 here and then it has 1s afterwards. And I find Qi4. Okay. Now I do this until I find n plus 1 such accepting states. So I continue until I find Qi n plus 1. So I create n plus 1 of these strings, and for each one of them, I find the first place where it's accepted. Okay, now here's the thing. My automaton A had only n states in it. But here I have n plus 1 accepting states, which means that at least 2 of them should be the same state. Okay, so just as an example, let's say that Qi n plus 1 is the same state as Qi2. I don't really care which 2 are the same. What I care about is that there are 2 states that are the same. Okay, but if this is the case, if these 2 accepting states are the same, it means that I started with this string and I got to this Qi2, right? And this was a prefix. I don't care about a finite prefix, but anyway, with a finite prefix, I got to Qi2. And then from Qi2, I could run this string and I could get back to Qi2, to the same place. Okay, so let's call this prefix P, and let's call this part here, which cycles from Qi2 to itself, let's call it R. Okay, now consider this string, P R omega, which means that I first do P, and then I just keep repeating R. Okay, what happens here? Well, P gets me to Qi2. And then every time that I'm repeating R, I'm going from Qi2 back to itself. So I'm going to see Qi2 infinitely many times. So this string has to be accepted by A. But the problem is that between each one of these accepting states, I had added a 0, right? So there is at least 1 0 in R. So this string has infinitely many zeros. So A is accepting a string that has infinitely many zeros. So that is a contradiction with the definition of A, because A was supposed to accept only strings that had finitely many zeros. And this contradiction shows that there is no such automaton A. You cannot have an automaton A if you want it to be, of course, a deterministic Büchi automaton. You cannot have a deterministic Büchi automaton A that accepts the same language as this non-deterministic automaton. Okay. Great. So the really important point here, and this is something that you have to remember, you don't have to remember all of this proof, but what you have to remember is that non-deterministic Büchi automatons are strictly more expressive than deterministic Büchi automatons. And why is it strict? Because, of course, if you have a deterministic Büchi automaton, it's also a non-deterministic Büchi automaton. So whatever you can get with DBW, you can also get it with MBW. But I just gave you an example of an MBW that models a language that no DBW can. Okay. And also we have the definition of regular languages, basically. So in the finite case, we say that the language is regular if there is a non-deterministic finite automaton that accepts it. In the infinite case, we say a language is omega regular if there is a non-deterministic Büchi automaton that accepts it. But it's really important that here we distinguish between NBW and DBW, and the definition of regular is using NBW. So we're always, by default, allowing non-determinism. So the next thing that you've probably again seen about finite automata is that if you have a finite automaton that accepts a language L1 and another automaton that accepts L2, there is also an automaton that accepts L1 complement, L1 intersection with L2, L1 union L2, and so on. So the question is, can we do these set operations on our Büchi automata? So first, let's consider the case of deterministic Büchi automata. So let's say that X is the set of all languages that can be recognized by a deterministic Büchi automata. Okay, so X is a set of languages. I put a language in X if I have a DBW for that language. Now, first I claim that X is not closed under complementation. So I cannot say that whenever a language L is in X, L complement is also in X. Why?
If it is accepted, then it should be included in the language that means nothing.
So basically what I'm saying is this: if the language L is in X, I can have another language, L complement, which is basically the set of all possible strings. So sigma omega, this is the set of all infinite strings, minus L. So everything that is not in L. What I'm saying is that if L is in X, I cannot necessarily say that L complement is also in X. This is not always the case.
Can we just find a counterexample to?
Sure. What is the counterexample?
That's the previous example you.
Yes, exactly. So we know that the language of this automaton cannot be shown by a DBW. But what was this language? This was the language of all strings that have finitely many zeros. Okay. What is the complement? The complement is the set of all strings that have infinitely many zeros. But you can have a DBW for the set of strings that have infinitely many zeros. Right? How can I do that? So I can just say I have an initial state. And if I read a 0, I go to this accepting state. Let's say this is accepting. Let me use blue for accepting. And from here, no matter what I read, I go back. This is a deterministic automaton, and it accepts all the strings that have infinitely many zeros. But we know that the complement language cannot be recognized by a deterministic Büchi automaton. So this means that X, so the set of languages that are recognizable by DBWs, is not closed under complementation. Okay. But let's do the positive things now. So I claim that X is closed under union, which means that if you have two different automata, let's say you have an automaton that accepts the language L1 and another one that accepts L2. There is another automaton that accepts L1 union L2. Can you prove that?
Yeah. I think it is in L1 union. After that, it should be in L1. By our assumption, it should be accepted.
Sure, but you have to create the automaton, right? So let's say I give you, let's say I have this language L1 and I have an automaton A1 that accepts L1. And I have a language L2 and an automaton A2 that accepts it. So I give you A1 and A2. Can you give me an automaton that accepts L1 union L2? And we are talking about deterministic automata.
Oh, determined.
Okay, let me ask you the same thing for non-deterministic automata first. So for non-deterministic automaton, let's say that, okay, first of all, for non-deterministic automaton, they're also closed under complementation. But for now, you have to just believe me on that. But they're also closed under union. So if I have a language L1 that is recognized by a non-deterministic automaton A1, and another language L2 that is recognized by A2, how do you create an automaton that accepts L1 union L2?
Just union.
Yeah. So I have these two automata, just put them together. And then for the starting state, say that I can start in A1 or I can start in A2. Right? And then let the non-determinism take care of everything. That's all we do here. So let me see what I have written here. Yeah. So let's say that this was my automaton A1. It had the set of states Q1. It had like initial states Q01 and so on. I just define the automaton A for the union to be an automaton that has the union of the states. And I'm assuming that these states are disjoint. So there is no state that is in both of the automata. Okay. So I just take a copy of each of these automata. And then for my starting point, I say you can start in automaton number 1 or you can start in automaton number 2. It's a non-deterministic choice. Right? And everything else is the same. Like the accepting states and the transitions, everything remain the same. Right? So basically this accepts the union because if a string is in the union language, then it's either in L1 or in L2. If it's in L1, I can start my automaton in A1, my run of the automaton in A1, and then there is a run in A1 that accepts. If it's in L2, there is a run in A2 that accepts. So taking union is really easy if you have non-determinism. But let's go back. What if you don't have non-determinism? So let's talk about deterministic Büchi automata. And again, I have a similar situation. I have A1 that accepts L1, A2 that accepts L2, and I want to create a new automaton A that accepts the union language. How would you do this? Right? And then what do you do with it?
Just mark each column, row, as the step.
Yes. Great. Okay. So basically, what we're going to do is that we're going to take the product. So I'm going to create a new automaton which has a new state for every possible pair of states in the first automaton and the second automaton. And then this new automaton is going to basically simulate both of the original automata at the same time. Okay, so I'm going to start at the starting state of both of them. And every time I'm going to say, okay, if reading a particular letter, the first automaton is going to state, let's say, Q1, and the second one is going to Q2, I go to the pair state, Q1, Q2. Okay. So this is basically an automaton that is simulating both of the original automata A1 and A2 at the same time. Okay, by taking the product and just, again, the transition function is also like the product. So the transition function says that if in the first automaton from the state Q, reading the letter A, you would go to another state, let's call it, I don't know, alpha. And then if in the second automaton, reading from the state Q prime, reading A, you were supposed to go to a state beta, then in this new automaton A, from the state Q, Q prime, because every state is a pair of states, reading A, you're going to this pair of states, alphabet. Okay? Again, this is nothing hard at all. I'm just simulating the two automatons, the two automata at the same time. Okay. Now, when should I accept? I should accept if either one of my original automata that I'm simulating are going to accept. So I should accept if I see T1, the set of accepting states in the first automaton infinitely many times, or if I see T2, the set of accepting states in the second one infinitely many times. And again, whenever I see T1, whenever I see an accepting state of the first automaton, I don't care where my second automaton is. So my accepting states are T1 times all the states in Q2. And then also Q1, which is like all the states in the first automaton times the accepting states in the second automaton. Yeah. So this is the same intuition he said, which is like we have a matrix, and if a row is accepting or a column is accepting, everything in it is accepting. Okay. Do intersection.
Oh, easy.
How do we do intersection? Why is it easy? It's not easy.
Thinking about it. Can I just change the condition to P1 and P1 product T2?
No.
Or no?
Yeah, so if I want to take the intersection, I cannot just say that I change my accepting states to T1 times T2. Because T1 times T2 is telling you that you have to visit T1 and T2 at the same time, right? But when I'm taking the intersection, I want to say that I want to visit T1 infinitely many times, and I also want to visit T2 infinitely many times. But they don't necessarily have to be at the same time. Maybe in every odd step, I see T1, and in every even step, I see T2. So the same kind of idea works in the sense that, well, intuitively, we understand that we have to simulate both of the automata, right? So I'm going to take the product automata. Okay. Yeah, so let me actually have some way of showing the product automaton. So let's say I show it with A1 times A2. This is the product automaton. Okay. And I'm not talking about any of the accepting states here. I'm just talking about the transitions and so on. So I have this product automaton. And when I wanted to do union, I could say, okay, if A1 accepts, wherever that A1 accepts is accepting. So if A1 accepted, then this entire row is accepting. And if A2 accepted here, then this entire column is accepting. So I could, for union, easily define my accepting states. But for intersection, I can't do that. So tell me what I should do for intersection. So again, I want to simulate both A1 and A2, but I want a run to be accepting if it sees both T1 and T2 infinitely many times, right? Previously, I just wanted to say if it sees either T1 or T2 infinitely many times, and that was easy. But now I need to see both of them infinitely many times. And I can't just take the product because I might not want to see them at the same time. Okay.
Then we should say Q1 times Q2 intersecting Q1 to Q2.
No,
Oh, no.
no,
Oh, no. Then Q2
that would not work either.
Q2. Oh,
So the problem here is that instead of just having one Büchi condition, I basically have two Büchi conditions, right? So I have a set T1 and a set T2, and I want to see both of them infinitely many times. But in the definition of Büchi automata, I can have only one Büchi condition. I can have only one set that should be seen infinitely many times. I'm going to give you a few minutes to think about this because it's a really cool trick. Let me give you a hint. If I want to see both T1 and T2 infinitely many times, I can alternate between them. I can say first I want to see T1. And as soon as I see T1, I can say, okay, now my goal is to only see T2. And then as soon as I see T2, I say now my goal is to see T1, and so on. Since I'm seeing all of them, both of them infinitely many times, I can also imagine that I'm alternating. Right, but not to the starting state. Because if you connect it to the starting state, you get something that wasn't a run in the original ones. But you're right. So whenever I get to an accepting state of one of them, I have to somehow switch to the other. Okay, here's another question. Let's say that I take A1 times A2, the product automaton here. And then let's say that I say my accepting states, T, are just anything that is an accepting state in A1. So it's T1 times Q2. So anything in A2, I don't care what's happening in A2. I only accept if it's accepting in T1. So this looks like a useless automaton, but actually you can use it as a gadget in your solution. So this is an automaton that is simulating A2, but it's ignoring the simulation, right? So it's accepting only based on A1. So it accepts the same language as A1, but with the side effect that it's also simulating A2. Okay, so let's say that I take a copy of this and I do the opposite there. So I take another product automaton, and in this one, I say that my accepting states are Q1 times T2. Okay, so this one is simulating A1, but ignoring the simulation and just accepting based on A2. Right? Now, why did I create these two automata? Because they have the same state space. And since they have the same state space, I might be able to somehow connect them together. So how would you suggest I connect these two automata? So this one accepts the language of A1, L1. This one accepts L2. How do you connect them so that you accept L1 intersect L2? The idea of alternation was that I start in L1, and if I get to an accepting state in L1, I say, let's switch to L2. So I take all the outgoing edges of this accepting state in L1, and if they were going to some vertex in L1, I just connect them to the corresponding vertex in L2. So I say, as soon as you get to an accepting state here, the next step is going to go to L2. And I'm going to do the same thing. I'm going to say in L2, if you get to an accepting state, the next state is definitely going to be in L1. Okay. Now, what this makes sure is that if I want to see the accepting states in L2 infinitely many times, I will also be forced to see the accepting states in L1 infinitely many times. Sorry, I shouldn't have said L1 and L2 because those are languages. But anyway, so if I want to see the accepting states on the right-hand side infinitely many times, the only way to do that is to also see the accepting states on the left-hand side infinitely many times. Because every time that I see an accepting state on the right-hand side, I'm forced to go back to the left-hand side. Right? And the only way I can come back is to see an accepting state. Yeah, so this basically gives us the intersection. Because now I'm forced to see the accepting states on both sides infinitely many times. Let's write this formally. Let's write what our graph is. No, sorry, what our automaton is. So it's going to have the same alphabet as the original automata. And instead of Q1 and Q2, my state space is going to be Q1 times Q2 times 1 and 2, because I have two copies. Right? Or instead of 1 and 2, I can write left and right. These are my states. Okay. Now, what is my transition function sigma? Okay. Sigma is like this. Let's say I'm at the state Q1, Q2 on the left-hand side. Okay. I just do a simulation. And let's say I've read the letter A. Okay. So there are two cases. Either Q1 was an accepting state, in which case I have to go to the right-hand side. Or it was not an accepting state, in which case I just continue my simulation. So this is going to be delta, this is going to be delta 1 of Q1, delta 2 of Q2, and remain on the left side if Q1 is not in T1. Right? So if I'm on the left-hand side and I have not reached a target of my first automaton, I'm just going to simulate both automata and just continue. But the other case is that this Q1 is actually in T1. And if that's the case, then I'm going to continue my simulation, but I'm going to now switch to the right-hand side. And this is if Q1 is in T1. So you see, I'm just doing my simulation. It's just that I have two copies. And in the left copy, whenever I reach a target of my first automaton, I switch to the right copy. In the right copy, whenever I reach a target of the second automaton, I switch back to the left copy. Okay. And I can write the same thing for R, right? So if I'm on the right-hand side and I read the letter A, I'm going to just simulate it. And I'm going to stay in the right-hand side as long as I'm not in a target. And if I am in a target and on the right-hand side, then I'm going to go to the left-hand side. T2 is in T2. Okay, these are my transitions. Again, this might look very complicated, but it's really not that complicated. It's just that I have two products. Each product is simulating both of the original automata. And I'm just saying that in the first one, I'm looking at the targets in the first automaton. And whenever I reach a target in the first automaton, I switch to the right-hand side. And then in the second one, in the right-hand side, I do the opposite. Whenever I reach a target of the second automaton, I go back left. Okay. Finally, what should be my target set in this entire automaton that consists of both of these products? It's enough to say that I want to see the target set on the right infinitely many times. Right? So I can just say this is T2, but I want it on the right. So it's like Q1 times T2 times R. That's my target set. So my target set are all the vertices on the right-hand side in which the second automaton that is being simulated is in a target. Okay. And why is that enough? Because we already saw that if we see these things infinitely many times, we have to see the targets on the left for the first automaton infinitely many times. All of these were about deterministic Büchi automaton. So we saw that DBWs are not closed under complementation, but they're closed under union and intersection. And intersection was a bit harder than union. Now, what about non-deterministic Büchi automaton? So for non-deterministic Büchi automaton, first of all, just believe me for now that they're closed under complementation. Just trust me. They're closed under union. I already gave you the proof of this. It's actually easier. You don't even have to take the product when you have non-determinism. You just say, take a copy of each of the automata and then say that I either start in the first automaton or in the second. Okay. They're also closed under intersection. Why are they closed under intersection? Well, this same thing works. Right? It's just that our products are also going to be non-deterministic. Okay. So you see, in some sense, non-deterministic Büchi automaton are kind of nicer to work with, right? Because we can complement them, we can take unions, we can take intersections, and they're more expressive as well. So we want to focus mostly on non-deterministic Büchi automata. But before doing that, one last thing that I want to say. So complementation is hard. And we will hopefully see one algorithm for complementation, and that's actually the contribution of Büchi, and that's why his name is all over the place. But it's not an optimal algorithm, and we have much better algorithms. We're not going to see the better algorithms in this course. We know that we can do complementation for MBWs, but it's hard. We know that we cannot do complementation for DBWs at all. But one nice question that is actually easy is, suppose that I give you a DBW, so I give you a deterministic Büchi automaton, and I ask you to complement it, but the complement automaton that you give me can be non-deterministic. Okay? So given an input DBW, output an NBW that accepts the complement language. Let's talk about this. This is actually easy. Let's look at this very special case. What's the language of this automaton? We solved this before. Yes. So it's the set of strings that have infinitely many zeros. And this one is the set of strings that have finitely many zeros. Right? And we've already seen that we cannot do this as a DBW, but it's an NBW. So this is my original DBW-A, and this is my MBW-B. And the language of B is the complement of the language of A. Okay. But how do I actually find B given A? So here's the thing. In A, what was the intuition here? I was saying that I'm going to ignore a prefix of ones, and then whenever I'm seeing a zero, I'm going to reach my target. And then I'll lose one letter. I don't care about that one letter that I lose. But again, whenever I see zero again, I will come back to the target. So when I want to complement it, in a sense, what I want to do is that I want to make a commitment. And the commitment is going to be that I'm not going to see zeros from this point onwards. And that's what this automaton does. So it says, do whatever you want for a finite prefix, I don't care. But at some point, you have to take this edge, and this edge is a commitment edge. And what that means is that you're committing that after you take this edge, you're not going to see any zeros anymore. Okay? And remember, 0 corresponded to an accepting state here. So essentially, what I'm saying is that at some point, I'm committing that I'm not seeing any accepting states of the original automata. Okay? So let's take this and let's actually extend it to the general case. So let's say I have my automaton A, and this was a deterministic Büchi automaton, and it has a set of accepting states T. Now I want its complement. In the original automaton, something is accepted, a run is accepted if it visits T infinitely many times. So in the complement automaton, I want to commit at some point to never see T ever again. Okay? So I'm going to use the same idea as before. I'm just going to take 2 copies. The first one is just my automaton A. The second one is my automaton A, except that I have removed all the vertices in T. Okay? And from every vertex here that had some transition, let's say I have vertex U here that had a transition to V. I'm going to add another transition that goes to the same vertex V, but in the second copy. Okay? So I can go from the first copy to the second copy, but I can never come back. Okay? And whenever I'm in the second copy, it's impossible to see T anymore because I've deleted all the vertices in T from the second copy. Okay? So basically, whenever I take an edge from the first copy to the second copy, I'm committing that I am no longer going to see a target in T from now on. Okay, that's how I'm doing the commitment. Okay, so basically, this means that a run is going to get to the second part only if it visits T finitely many times and not infinitely many times. So next, what I'm going to do is that I'm going to say everything in this second part, this is my target set now. So my goal is to get to the second part and just remain in the second part forever. Okay? This gives me the complement automaton. And it's just a matter of following the definitions now. Because basically in the original automaton, in order to get accepted, a run had to visit T infinitely many times. In this complement automaton that I created here, in order to get accepted, a run has to commit at some point after a finite prefix to never see T. Right? Which is, of course, the complement of seeing T infinitely many times. Okay. So yeah, that's it for this session. We saw that if you have a DBW, it's possible that you cannot complement it and get another DBW, but you can always get an NBW as the complement, and it's easy to compute that. Was the definitions of automata on infinite words. We especially saw deterministic and non-deterministic Büchi and parity automata. And we also said that we say a language is omega regular if there is a non-deterministic Büchi automaton that recognizes that language. And then we talked about whether these languages are closed under set operations. So for the deterministic case for DBWs, we saw that they are closed under union and intersection, but not under complementation. So it's possible that you cannot take the complement of a DBW as another DBW. So we also saw that non-determinism really matters, and NBWs are strictly more expressive than DBWs. And finally, we saw that the languages of these NBWs are closed under union and intersection. I also promised you that they're closed under complementation. Hopefully, either today or in the next session, we will see why. Okay, but let's talk about complementation a little bit more. The last thing I showed you in the last session was how to take the complement of a dBW to get an NBW, right? So the fundamental intuition that you have to understand here is why this doesn't work if our original automaton is non-deterministic. So if my original automaton A is an NBW, a non-deterministic Büchi automaton, why can't I just apply the same kind of argument where I take two copies of A and I just delete T, the set of target vertices in one of them, and then I do this. I say that from each vertex, you can either have the transition that you already had in A, or you can transition to the new copy, and that transition is the same as committing that you will never see T. Okay, so intuitively, it seems this should work even if I have non-determinism in my original A. But it doesn't. Why doesn't it work? So here's the thing. When the original automaton A was deterministic, for every word, we had exactly one run, because that's the definition of determinism. So I could say that that one run has to eventually go to the second part. And that's what I did here, right? So I set my new target set to be everything that is in this second part, right? So what I was saying before was that, okay, you have a single run, and that run has to come here in order to get accepted. And any run that would stay in A would not be accepted, of course. Okay. But now, if A is non-deterministic, the problem is that I can have many different runs in A over the same word, right? And if I have many different runs, some of them might go to the right-hand side and commit to never seeing T again. But that's not enough, right? Because even if I have one run that goes to the right-hand side and never sees T, this construction is going to accept it. But on the other hand, even if I have just one run that stays in A and sees T infinitely many times, A is going to accept that. It's possible that on the same word, I have both of these runs. I have a run that just remains in A forever and sees T forever. And I have another run that goes to the right-hand side and never comes back because of the non-determinism. And that basically means that this construction will not work if I have a non-deterministic A. It goes back to the fact that, okay, another way of looking at this is, suppose I have a word that is accepted by A. It means that there was one run in A that was accepted over this word. So if I want to compute the complement of A, I have to make sure that none of the runs over this word are accepted. So previously, since I had just one run, I could just make sure that that one run is not accepted anymore. But here I cannot do it because I have many different runs. Okay, but let's get back to the main point of this session. So we're going to talk about several classical problems, and we're going to talk over Büchi automata. So the first problem is emptiness. So I give you an automaton, and I ask you, is the language of this automaton empty? Does this automaton reject everything, or does it accept something? That's emptiness. The dual of emptiness is universality. So I give you an automaton, and I ask you, does this automaton accept everything? Or is there a string that is not accepted by this automaton? Then we have complementation, which is actually the main problem that we want to talk about. So I give you an automaton A, and it can be deterministic or non-deterministic, I don't care. I want you to find another automaton B such that the language of B is the complement of the language of A. This is the main problem that we have to solve. And finally, we have containment. And containment is easy. It's like I give you two different automata, A and B, and I ask you, is the language of A a subset of the language of B? Okay. So can you tell me how I can solve containment if I have solutions for the previous three problems? So what does it mean for the language of A to be a subset of the language of B? This happens if and only if the language of A has no intersection with the complement of the language of B. But that's the language of B complement, if I can compute B complement. Okay, so this should be empty. So basically, if I can do complementation first, and then I can do intersection, and then emptiness, I can answer containment. Okay. I already know that I can do intersection. We've seen how to do intersection. So we can do intersection. But if I want to answer whether the language of A is a subset of the language of B, I first compute B complement and then take its intersection with A. And then I ask an emptiness question. I ask, is this automaton accepting anything at all? Okay. So basically, I'm going to put a check mark here. I'm going to say we solved containment, because if we have the solutions for the rest of them, then containment is also solved. But now let's actually talk about emptiness, universality, and then if we had time about complementation. So emptiness, I give you a deterministic or non-deterministic Büchi automaton, and I ask you, is the language of this automaton empty? Or another way of looking at it is to look at the opposite question. Is the language of this automaton non-empty? Does this automaton accept something? Okay. How can you answer that? So for this automaton to accept something, let's say I want to say that there is a word W that is accepted by this automaton. For this automaton to accept W, there should be an accepting run of the automaton over W. And an accepting run is a run that visits my target set T infinitely many times. So it has to visit the accepting states, the blue states, infinitely many times. So basically my question is, let's look at this automaton as a graph. Is there a path in this graph starting from one of the initial vertices that sees these other vertices, these blue vertices, infinitely many times? Do I have a path in my graph that starts at the initial vertices and visits T infinitely many times? How can I answer that? Well, I can just think of it as a game, right? So look at this same graph. Let's say this is a Büchi game. And the objective of player one is to visit the blue states infinitely many times. And let's say that that all of the vertices belong to player one. So it's like a one-player game. It's a special case of the two-player games and graphs that we've seen before, where all vertices are controlled by player one. So player one can do whatever he wishes. And the question is, can he visit the target states infinitely many times? This is a special case of a Büchi game. It's actually a single-player Büchi game. And we've seen that we can solve Büchi games in polynomial time. We had both ONM and ON squared algorithms for that. So this shows us that emptiness of an automaton can be checked in polynomial time, because it's just asking for winning sets in a Büchi game. Okay, nice. Can we do better than this? Can we have a better runtime than n squared? So here's the thing. Let's say that I have an infinite path that sees my target vertices infinitely many times. First of all, I have a finite number of target vertices, right? So there should be one particular target vertex that is seen infinitely many times, right? But if a particular target vertex is seen infinitely many times, it means that I'm going through cycles that start and end at the same vertex, right? And every time I might go through a different cycle, but I don't have to. I can just take a single cycle. So in other words, I can guarantee that I will see my target vertices infinitely many times if I can find a cycle that contains one of my target vertices. And then I'll just go to that cycle and cycle around, right? So what are the conditions that I need? Well, the first condition is that I need there to be a cycle. The second condition is that I want that cycle to contain one of the blue vertices. And finally, I want that cycle to be reachable because I have to be able to reach it from my initial states. If I cannot reach it, it's a useless cycle, right? So if I find a cycle like that, I'm happy. Now, in order to do that, I can just look at my strongly connected components, okay? So I take my graph, the graph of my automaton, and I look at its decomposition into strongly connected components. So let's say these are my strongly connected components. This is strongly connected component 1, 2, 3, and let's say 4. And then I have some edges between some of these as well. Okay. Now, first of all, I remove all parts of the graph that are not reachable from the initial states. How can I do that? Easy. I just do a DFS from my initial states. I remove everything that is not reachable. Then I find my strongly connected components in the reachable graph. So now here I'm sure that everything is reachable from my initial state. So now the only question I have to answer is there a cycle that contains a blue vertex? Well, that's the same as saying, is there a strongly connected component that has a blue vertex? Because if one of these strongly connected components has a blue vertex in it, I can just go there to this blue vertex. And then from this blue vertex, I can just remain in the same strongly connected component and go back to itself. But there is just one corner case, and that's that it should be a non-transitional strongly connected component. So it should be a strongly connected component which has at least 2 vertices. I have a bad case, which is this. Let's say I just have one vertex and it's its own strongly connected component. I can enter it, I cannot remain, I have to pass. Okay, other than this case, if I have a strongly connected component with one vertex that has an edge to itself, or if I have a strongly connected component with more than one vertex, I'm happy. Because I just find this vertex, and then I just go around in this strongly connected component, and I come back to this vertex, and I just keep cycling. Okay. How much time do I need to do this? Well, I need to do a DFS first to find all the reachable states. That's linear time, n plus m. Then I need to find the strongly connected components. Hopefully you've seen this in 3711. There is an algorithm of Tarjan, which actually also uses DFS to find strongly connected components. That's also linear time. And then finally, I have to just go over my strongly connected components and see if they're non-transitional and if they have a blue vertex in them. So linear time also. Okay, great. So emptiness of deterministic and non-deterministic Büchi automaton can both be checked in O(n) plus m, where n is the number of vertices and m is the number of edges. Okay. So you might think that since emptiness is easy, then universality should also be easy, right? Because if you think about it, here I was asking, does this automaton reject everything, or is there something that is accepted, right? Whereas in universality, I'm asking the opposite question. I'm asking, does this automaton accept everything, or is there something that is rejected? But actually, universality is much harder. So first, let's talk about the deterministic case. Okay. So let's say I have a deterministic Büchi automaton A, and it has n states. And I want to figure out if the language of A is the set of all infinite strings. I want to figure out if my automaton accepts everything. Okay. So let's just go over this definition several times, and we will eventually get to an answer. So if the language of A is everything, it means that every infinite word W is accepted. But if every word W is accepted, it means that every run of A is accepting, because this is a deterministic automaton. So every word has a unique run, and every run has a unique word. Okay? So I basically want to see if every run of A is accepting. Now I say let T be the set of accepting states in A. Of course, a run is accepting if it visits T infinitely many times. So if I want to check whether all of my runs are accepting, what I'm asking is, do all infinite paths go through T infinitely many times? Or is it possible to have an infinite path that visits T only finitely many times? This is my question now. Okay? So I want to decide if I'm in this case or in this case. The first case is that every infinite path visits T infinitely many times. The second case is that there is an infinite path that visits T only finitely many times. But now this is a Büchi game. So let's just take this graph of my automaton again, and let's say that it's a single player Büchi game. So it's a Büchi game, but all the vertices belong to player one. And player one wants to make sure that we visit the target vertices only finitely many times. Okay? So again, a single player Büchi game is solvable in order n squared or nm time. We've seen this before. So universality of deterministic Büchi automata is actually decidable, and it's decidable in polynomial time. So we could solve this in polynomial time. Okay. But another way of looking at this is that I want to figure out if every infinite path visits T infinitely often, right? So consider an infinite path. I have a finite graph. Since I have a finite graph, this infinite path has to go through a lot of cycles, right? It actually has to go through infinitely many cycles, because there is at least one vertex that is seen infinitely many times. Okay. Now, consider all the cycles, consider all the simple cycles, let's say. I have finitely many cycles, but I have an infinite path. So there is at least one cycle that is seen infinitely many times, right? So here's the question that I basically have to answer. I have to answer if every reachable cycle has a target vertex. And I claim that this is equivalent to my problem. Why is it equivalent? So if there is a cycle that I can reach and doesn't have a target in it, then I can just go to that cycle, and then I can keep cycling forever. And then I will see my targets only finitely many times, only in the prefix that I had before I reached this cycle. Okay? But if every reachable cycle has a target vertex, then every infinite path has infinitely many of these cycles in it. I can decompose it into infinitely many cycles, and each one of them is visiting the target at least once. So I'm forced to see the target infinitely many times. So basically, these two are equivalent. I basically have to figure out if every reachable cycle contains a target vertex. Okay? How can I do that? Give me an algorithm. So forget the algorithm for Büchi game. I mean, of course, that worked. But I have a graph. I have marked some of the vertices as blue. And the question is there a reachable cycle that does not have blue vertices in it? Or is it the case that all reachable cycles have blue? Again, just like before, I first remove the part of the graph that is not reachable. Just do a DFS, get rid of the non-reachable part. So now the question is, do all of your cycles have a blue vertex in them? Okay, remove the blue vertices, check if you have any remaining cycles. Right? You just delete them, and checking if you have a cycle is also another DFS. So again, you can solve this in linear time. So universality of deterministic Büchi automaton can be solved in linear time. But it's very important to see that the same argument does not work for non-deterministic Büchi automata. Because the main step, the thing that really made everything easy, was this step. Okay? I said that if all of the words are accepting, then all of the runs are accepting. This is because I had a one-to-one correspondence between runs and words. That only exists in deterministic automata. In a non-deterministic automata, I just can't say this. I cannot say that every run should be accepting. Because maybe I have a non-deterministic Büchi automaton that accepts all the words, but for every word, it has many different runs, and some of those runs are accepting and some of them are not accepting. Okay? So universality of deterministic automata is much easier than universality of non-deterministic automata. And actually, I'm going to show you that this is a really hard problem. I'm going to consider the opposite problem. I'm going to consider non-universality. So I give you an automaton as input. You should output 1 if this automaton is not universal, and you should output 0 if this automaton is universal. This is called the non-universality problem. And I'm going to prove that this problem is NP-hard. Okay. So we went from linear time in universality for deterministic Büchi automaton to NP-hard for non-deterministic Büchi. Okay, if I can prove this claim, then the corollary that we have is that we cannot really hope for any algorithm that would find the complement of a non-deterministic Büchi automaton in polynomial time. Why is that? Because if I could find the complement in polynomial time, then I could do emptiness checking in linear time on the complement, and that would solve universality and non-universality, both of them, right? So basically, if you find an algorithm that complements a non-deterministic Büchi automaton in polynomial time, you have proven that P is equal to NP. And this is, of course, a big open problem, and I don't expect any of you to solve it. So okay, we cannot really hope for a p-time complementation. But let's prove our claim. Let's prove the claim that non-universality of MBW is NP-hard. Now, how do you prove NP-hardness? You prove NP-hardness by a reduction. That's always the case, right? So, I mean, yeah, you have other ways of proving it too, but normally you always prove it by reduction. So I take another problem that I know is NP-hard, in this case, 3 coloring, which is one of the classical NP-complete problems of CARP, the first 21 problems that were shown to be NP-complete. And I'm going to give a reduction from 3 coloring to non-universality of MBW. And what that means is that if you give me a polynomial time algorithm that takes a non-deterministic Büchi automaton and tells me whether it's universal or not, I can use that algorithm to decide whether a given graph can be colored with 3 colors in polynomial time. And because we think we cannot do 3 coloring in polynomial time, so we think we cannot do non-universality in polynomial time. Okay. Let's just go over the definition really fast. So 3 coloring the problem is that I've given you a graph G as input, and you can assign one color to every vertex. And you have only 3 colors. You have red, green, and blue. And you want to make sure that no 2 neighboring vertices have the same color. This is 3 coloring. And I mean, the output is always yes or no. We're always talking about decision problems. So I don't actually need you to give me the coloring. It's just you're going to tell me if it's possible or not possible. Okay. And without loss of generality, we're going to assume that the graph G is connected. Because if I give you a disconnected graph, you can just color each of its connected components separately. So it doesn't really make that much difference if I ask about a connected graph or a general graph. Okay. So here's what I'm going to do. I have to create a non-deterministic Büchi automaton. So the first thing I have to define are the letters of my alphabet. And I'm going to define the letters of my alphabet like this. I'm going to say that my alphabet is V times RGB. So every letter of my alphabet is a pair, where the first part of that pair, the first coordinate, is a vertex in my graph, and the second coordinate is a color. It's either red or green or blue. And this whole thing is just one letter of my alphabet. Okay? So when I talk about infinite strings, I'm talking about infinite sequences of pairs like this. That's what I'm going to do. And now I'm going to define a lot of different NBWs using this alphabet that basically is the alphabet of vertices and colors. Okay. Well, before I do this, let me give you some intuition. I want to create an NBW, and I want to say that my NBW is non-universal if and only if my graph is 3-colorable. Okay? So if I have a connected graph, one way that I can prove to you that this graph is 3-colorable is if I give you an infinite path on this graph, where at every step, I tell you which vertex I am at and which color the vertex is, right? I mean, it's a very wasteful way of proving to you that this is 3-colorable, but if I give you such a path, if I give you an infinite path, and if this path goes over all the edges of the graph, and if at every step of this path the color changes, then you would be really convinced that this graph is 3-colorable. Okay. So another way of seeing this is that the graph is 3-colorable if and only if there is such a path, such an infinite path that has all these nice properties. So what I'm going to do is that I'm going to create a non-deterministic Büchi automaton that accepts all the paths that don't have these nice properties. And then I ask, is this automaton universal or not? And if this automaton is not universal, then it means that there is a path that satisfies all of those properties, which means that the graph is 3-colorable. Okay? Now, this might seem like a lot, but let's just go through it and you will see what I'm going to do. So this was just an intuition. I'm going to define several different automata. And remember that the input to my automata is always an infinite sequence where every element of that sequence is a pair. And the first element of the pair is always a vertex in my graph, and the second element is a color. Okay. So my first automaton, A, is an automaton that ignores colors completely and just accepts any sequence of vertices that is not a valid path in G. Okay? So generally, I want to create automata that accept non-desirable paths. Okay, so the first thing I do is that I say, if you give me something that is not a path, I will accept it always. And that's the role of automaton A. So for example, let's say this is my graph and my 3 coloring. Let's say this is my first path, 4R, 3R, 2G, and then 1B and 6B just repeated. My automaton ignores the colors. It doesn't care about colors. So it checks that from 4, I can go to 3. From 3, I can go to 2. From 2, I can go to 1. From 1, I can go to 6, back to 1, back to 6, back to 1, so on. So this is a valid path. So my automaton rejects it. Okay. Whereas if I have a path that starts like this with 4 and 8, from 4, I cannot go to 8. This is an invalid path. So my automaton accepts it. Okay, how can I create this automaton? Well, it's actually quite easy. So what I'm doing here is that I'm turning my graph into the automaton. So I'm going to say that my set of vertices, the set of states in the automaton, are just the vertices in the graph with 2 additional vertices. I add a vertex Q0, which is like my initial state. And I also add this down, or I don't know, bottom state, which basically shows failure. And I start at Q0. Now, whenever I read something, so if I'm at state Q0 and I read the letter VC, I just go to state V, which means I'm now at vertex V. I want to continue my path from there. If I'm at state U and I read VC, I go to V if there is an edge from U to V in the graph. But if there is no edge from U to V in the graph, I go to this bottom state. So whenever I reach my bottom state in the automaton, it means that this wasn't a path in the graph. Okay? And from the bottom state, I always remain in the bottom state, no matter what I read. And then my accepting states, T, is just my bottom state. So my automaton accepts anything that gets stuck, any path that cannot really exist in the original graph, which is exactly what I wanted. So my automaton A accepts any sequence where ignoring the colors, the list of vertices is not a valid path in G. Okay, that was my first automaton. I'm going to create 5 automata, and you have to remember all of them. Okay. So my second automaton, I'm calling this automaton B, and it's kind of the opposite of the first one in that it ignores the graph and it only focuses on the colors. Okay. And it accepts all the words in which there is a vertex that appears with 2 different colors. Because ideally, I don't want the color of a vertex to change. So I say, if you give me a sequence, and in this sequence, the color of a vertex does change, that's terrible. And again, remember, my automata are going to accept everything that is terrible. So B is going to accept it. So for example, here I have a sequence 1R, 3B, 4G, 1R, 7B. Okay. In this sequence, 1 is always appearing with the color red, 3 is always blue, 4 is always green, 7 is always blue. So this is rejected by B. Whereas in this one, 1 is red here, and then 1 is blue here. So this is accepted by B. Okay. How do I create such an automaton B? So basically, I want to accept if I see the same vertex with 2 different colors. That's actually exactly the idea here. So I have a starting state Q0. And remember, I can have a non-deterministic automaton. So I can have a transition from Q0 to itself, which says like, whatever, you can always do this in transition. And then for every vertex and every color, I do this. I say there is 1R, and then I can ignore whatever, some suffix here, and then I take 1B. And this is an accepting state, and it has an edge only to itself. So if anywhere in my sequence I see 1R and later on I see 1B, this automaton will accept it because it will see this state infinitely many times. And then I do the same thing for 1R and 1G, and then 1B and 1R, and so on, for all of my vertices and all of my color combinations. So this makes sure that if I see the same vertex with 2 colors, I will definitely accept. Is this clear to everyone? Nice. Next one. So I want my next automaton C to accept all the words which do not contain all the edges of the graph. Okay, so this one is again ignoring the colors. Because if I have like an infinite path, there are two cases. Either it sees all the edges of the graph or it misses some edges. And I want to accept those paths that miss at least one edge. Again, it's kind of similar. I mean, it looks more complicated, but it's actually very similar. So let's say I want to create an NBW that accepts every path that does not have UV or VU in it. So look at this. It starts here, and as long as the thing that we are reading is neither U or V, it remains here. And if it reads a U, it will go to this state, and it will remain there as long as it reads a U. And if it reads a V, it will go here. By the way, this is a deterministic automaton. So if I have UV, I will end up here, and that's the only path because this is deterministic, and I will reject. Similarly, if I have VU, I will end up here, and because my automaton is deterministic, I will also reject because that's the only path. Okay, so this is an automaton that rejects any string that has UV or VU in it. Okay, so I just create one of these for each one of my edges, and then I take the union of all of them. Right, and that's going to be my automaton C. And the automaton C accepts all the words which do not contain all the edges of the graph. So it accepts any sequence that misses at least one of the edges of the graph. Is this clear to everyone? Okay. I promise we're getting to the end of it. So I have another automaton D, and this one ignores all the vertices, but it accepts all the words that have the same color twice in a row.
Oh.
Yeah, so right after each other. So for example, it accepts this one because it has two red vertices right after each other. And it rejects this one because it goes red, blue, red, blue, red, blue. Okay, how do I create this automaton? Well, it's quite easy, really. It's the simplest automaton that we have. Right? It's like if I see R, I get here and I accept. If I see GG, I get here. If I see BB, I get that. Okay. Now, finally, let me define my automaton E to be the union of all these four previous automata that I defined. So I define E to be A union B union C union D. So what does E accept? E basically accepts any sequence where one of these things happens. Okay? We will get back to that. But before actually doing that, let me go through the claim. My claim is that this automaton E is universal if and only if G is not three-colorable. Or another way to say this is that E is non-universal if and only if G is three-colorable. Okay. So here's the thing. When does E accept an infinite word? It accepts it if either A or B or C or D accept it. Okay? But A accepted all the words that were not a valid path. B accepted all the words that do not assign a unique color to each vertex. C accepted all the words that do not visit some of the edges. D accepted all the words that had two simultaneous vertices with the same color. So if I have something that is not accepted by any of these, if I have a sequence that is not accepted by E, that sequence is a valid path on G. It assigns a unique color to every vertex. it visits all of the edges, and whenever it traverses an edge, the color is changing. So if E does not accept a particular string, that means G is tricolorable, and vice versa. So yeah, E is non-universal if and only if G is tricolorable. And we know that tricolorability is NP complete, so non-universality is NP hard. Yeah, I mean, the other side is also quite easy to prove. Like, if you do have a valid tricoloring, you can create an infinite path that goes through all of the vertices with the right colors, and then that path will not be accepted by E. Okay. Now, before going there, what did we just see? We saw that complementation of deterministic Büchi automaton is actually quite easy. We had an easy way to do it. This was the way, and it was polynomial time. But then we saw that we cannot complement non-deterministic Büchi automaton in polynomial time, of course, unless P equals NP. We don't know. If P is equal to NP, then maybe you can do it. But if you can do it, you've also proven that P is equal to NP. And that's because non-universality is NP hard. Okay. But anyway, I want to complement my non-deterministic Büchi automata. Who cares if I can't do it in polynomial time? Can I do it at all? So if I give you a non-deterministic Büchi automaton A, and I ask you to construct another non-deterministic Büchi automaton B, such that the language of B is the complement of the language of A. I know unless P equals NP, you cannot do it in polynomial time. But can you do it at all? Like, if I give you as much time as you like, I just tell you your algorithm has to terminate. You cannot run forever. Can you give me a complement? And the answer is yes. And actually, this is the theorem of Büchi. But the algorithm of Büchi, which is the algorithm we're going to see, is not optimal. It's actually, I think, going to take doubly exponential time, which is terrible. But now this is the part where I'm going to surprise you. Hopefully, you've passed some courses on graph theory and you know about Ramsey theory. Okay. No one expected this, but yeah, we're going to use Ramsey theory for this. By the way, if you want to see faster constructions of this, look into the works of Nir Peterman. He has better constructions of this. But yeah, I'm going to just give you the original thing by Büchi, and that's as deep as this course goes. We will not go deeper than that. Okay, so let's just do some background in graph theory. If I have a graph with 6 vertices, if I have a complete graph on 6 vertices, and I color each one of the edges either red or blue, there is definitely a triangle that is monochrome, that has all of its edges in the same color. Okay. Now, one proof of this is this really nice figure that I stole from Wikipedia. Someone actually just tried all the cases and showed that in every case you have a triangle. But an easier thing to do, an easier way to prove this is using the pigeonhole principle. So let's say I have 6 vertices. I take my vertex number 1, and there are 5 edges going out of this, right? So by the pigeonhole principle, at least 3 of these edges are the same color. Let's say at least 3 of them are blue. So I know that from vertex 1, I have at least 3 blue edges going out. I have 2 other edges, I don't know their color. Okay. So I look at the endpoints of these edges. If 2 of these 3 vertices are connected with another blue edge, I immediately have a blue triangle, right? So the only way that I don't have a blue triangle is if all of these vertices are connected with red edges. But then that gives me a red triangle. So in any case, I have a monochrome triangle, a triangle of just one color. Okay? This was easy. This was just applying the pigeonhole principle. Nothing hard about it. What happens if our graph is infinite? Let's talk about Ramsey's theorem for infinite graphs. So let's say that I have a complete infinite graph G. So I have a graph G on infinitely many vertices, and it's a complete graph. I have an edge between every pair of vertices. Okay? And let's say that instead of 2 colors, I have C colors. But C is just a number. It's like a finite number. I've colored every edge by one of these C colors. The theorem is that there is an infinite monochrome clique in G, which means that there are infinitely many vertices, such that if you take the subgraph on only those vertices, all the edges are the same color. Okay? So the proof is actually an extension of the simple proof by pigeonhole principle that I gave you here. It's very similar. So just as before, I'm going to first take one vertex and I'm going to call that A1. I take this one vertex and I say, okay, there are infinitely many edges going out of this vertex, but I have only a finite number of colors. So there should be at least one color that is used for infinitely many of the outgoing edges. I'm going to call that color C1. Okay, so A1 was just a vertex that I arbitrarily picked, and C1 is a color that appears infinitely many times on the edges that are connected to A1. So I'm going to take the other side of all of these edges, and I'm going to call that vertex set V1. So V1 is the set of all vertices that are connected to A1 with the color C1. Okay. Now, I'm just going to remove all of my other vertices. I'm going to say I'm only keeping V1 and getting rid of all the other vertices in my graph. So I look at the induced subgraph on V1, G of V1. This is also a complete graph because our original graph was a complete graph. Now I do the same thing again. I say this is an infinite graph. I can pick a vertex A2, and then I can say that there are infinitely many edges going out of A2. So there is a color that appears infinitely many times. Let's call that C2. And let's take the endpoints of all the edges with color C2 that are going out of A2, and let's call that V2. And let's erase everything else from the graph and just keep V2. Again, V2 is infinite, so I can do the same thing. So I can do this same thing forever. And if I just continue this process forever, I get 3 infinite sequences. I get a sequence of A's, which were the vertices that I picked every time. I get a sequence of C's, which were the colors. And I get a sequence of V's, which were like the remaining vertices, the vertices that I kept in my graph and did not delete. Okay. Now, again, I'm going to say I have finitely many colors, but these are infinite sequences, especially this one. This is an infinite sequence. So there is some color, let's call it C prime, that appears infinitely many times in my C sequence. Okay. So let's consider all the indices where C prime, this infinite color, appears. Okay. And let's take all the vertices corresponding to them. So I'm going to say V prime, this is my definition. I'm going to define V prime as the set of all vertices AI such that the color that I picked for AI was this C prime. Ci was equal to C prime. Okay. Remember, the color that I picked for AI was a color from which I had infinitely many edges going out of AI. Okay. Now, my claim is that this V prime is an infinite monochrome clique. First of all, V prime is infinite. Why is it infinite? Because by definition, C prime appeared infinitely many times. And so I have infinitely many AIs in V prime. So it's infinite. Of course, it's a clique because every induced subgraph is a clique because my original graph was the complete graph. I have to prove that all the edges are monochrome. I actually claim that all of the edges that go between two vertices of V prime are of the color C prime. Now, why is that? Because let's say that AI was of this color C prime, and then I had VI here. And then let's say AJ is another one, another vertex that is of the color C prime, and I had VJ here. So when I had VI, VI was the set of all vertices that were connected to AI with the color C prime. And I deleted every vertex that was outside of VI. The fact that AJ still remained there means that AJ was in VI. And if AJ was in VI, it means that the edge from AI to AJ had the color C prime. And this works for every pair of vertices in V prime. So all the edges in my V prime are of the same color and they're of the color C prime. Okay. I just want you to step back and just appreciate what we just proved. I'm telling you that if we have a graph with infinitely many vertices, and it's a complete graph, and we color each one of the edges with one of the colors from 1 to C, then inside this graph, you can find infinitely many vertices such that all the edges between them are of the same color. It's really amazing. So anyway, there is an infinite monochrome clique in G. Okay. What does this have to do with non-deterministic Büchi automaton? You might think like I'm just making fun and telling you something completely irrelevant, but let's actually get back and let's see the amazing proof of Büchi. And just every time I see this proof, I'm amazed at how he got to this. It's such a non-trivial thing, but at the same time, it's really easy to explain. So let's say I want to complement an NBW. So I'm given an NBWA, and I want to construct another NBWB such that the language of B is the complement of the language of A. Okay. So here's the first step. I say it's too hard to reason about infinite words. So let's instead try to reason about finite words. So I define an equivalence relation over all non-empty finite words. So all the words in sigma plus, all the words that are finite but not empty. Okay? And I use this to denote my equivalence relation. So basically, I want to say that V is equivalent to W if I can do replacement. If whenever I have a string and somewhere in that string I have V, I can just cut V out and put W in its place. Okay? So again, imagine this. I have an infinite string. I'm giving this infinite string to my automaton A. Okay? Now I want to do some small surgeries. I want to say, I go over this string, and whenever I see V, I just delete V and put W instead. But I want to do this in a way that makes sure the behavior of my automaton does not change. Okay? So based on that intuition, here's the formal definition. So I say that V is equivalent to W if these two conditions hold. The first condition is that if there were a pair of states Q and Q prime in my automaton, such that I could go from Q to Q prime using the word V, I should be able to go the same between the same pair from Q to Q prime using the word W. Does that make sense? So I'm saying previously I could be at state Q and read the word V, and that would transition me to Q prime. If I want to replace V with W, I want to have the same kind of transition. And it's also if and only if. Okay? Now, the second thing is also very similar, except that I want to also keep track of whether I've seen one of my accepting states on the way. Because here's the thing. It's possible my initial string was just v infinitely many times. Okay? And maybe I always started at some state q and went to some state q prime. But maybe when I was reading v on the way from q to q prime, I saw an accepting state. But if I replace the v with a w, I don't see an accepting state. In that case, I cannot really replace v with w. Because instead of this, I will get w. And this one is accepted by my automaton. This one is rejected by my automaton. So this is my second condition. I say that for every pair of states q and q prime in my automaton, if there is a run from q to q prime using the word v that also visits my target states, then there should also be a run from q to q prime using the word w that also visits my target states. And again, this is if and only if. So that's what I mean when I say two finite strings v and w are equivalent. I basically mean that, again, the intuition is I take v, I replace it with w, nothing changes. But the formal definition is that for every pair of states, I can go from q to q prime using v if and only if I could go using w. I can go from q to q prime using v and see a target on the way if and only if I could do the same thing using w. Okay. So, answer this question. How many equivalence classes do I have? Do I have finitely many equivalence classes, or do I have infinitely many equivalence classes?
Finite.
Okay, why is it finite?
Wait.
The answer is actually on the slide, but
Oh, is it because we have only finite number of alphabet is sigma derivative?
well, the alphabet is finite, but you see these are not letters of the alphabet, right? So V and W are finite words themselves. So they're members of sigma plus. And sigma plus is an infinite set, because you have infinitely many finite words. Yeah, so at the first glance, it feels like we can have infinitely many equivalence classes, because it feels like I have equivalence classes over sigma plus, and sigma plus is an infinite set. So it's possible to have infinitely many equivalence classes. But here's the thing. I can basically encode each one of my equivalence classes as some sort of function. Let's say I have a word v. What does this equivalence relation mean? It means that the only things that I care about this particular word v are two things. First of all, from every state q, which other states q prime can be reached using v? And secondly, from every state q, which other states q prime can be reached using v while also visiting t? These are the two things that I really care about. If these two properties are the same for v and w, I say v and w are equivalent. They're the same equivalence. So I can show every equivalence class by a function that takes a state and gives me two sets of states. It takes a state q and gives me the set of all states that can be reached from q using v. Okay, so this is like the set of reachable states, I would say, reachable using v. And the set of states that are reachable using v, but I can also see a target on the way. So I call this target reachable using v. Okay. So for every v, I can basically have a function f of v that gives me these two sets. That tells me from every vertex, if I apply v as the input, what are the other states that I can reach, and what are the states that I can reach, and I can also see a target in between. So this function, I call it f of v. And basically, you can just do definition chasing. V is equivalent to W if and only if f of v is equal to f of W. V is equivalent to W if and only if f of v is equal to f of W. So basically, when I'm asking you how many equivalence classes you have, I'm asking you how many functions like this you can have. And now it's obvious that it's finite, right? Because Q is a finite set. So 2 to the power of Q, the subsets of Q, that's also a finite set. So 2 to the Q times 2 to the Q is also a finite set. So you have the number of functions from a finite set to a finite set. It's finite. It's huge, but it's finite. So, yeah, we have finitely many equivalence classes. And let's say that I show the equivalence class of the function f with L of f. So L of f is a language. It's a set of strings, but it's a set of finite strings, right? Because we defined our equivalence relation over finite strings. So L of f is a set of finite strings. So the next question is this language regular? Because whenever I have a set of finite strings, I want to ask, is there a non-deterministic finite automaton that accepts this set? Or a deterministic finite automaton that accepts this set? Is it a regular set? Yes or no? So another way of looking at this is that I give you a function f, okay? And this function f is basically a map that maps every state to two things. Everything that is reachable from that state and everything that is reachable and can also see a target on the path when reaching. And now my question is, if I give you this function, can you create an automaton so that when I give you a word, when I give you a finite word to this automaton, the automaton accepts if and only if that finite word satisfies the requirements of this function. If and only if f of v is equal to f. Okay, so what is this function? This function is basically giving you a bunch of constraints. It's saying that I want to accept words such that, for example, if I start at the state u and I apply this word, I can get to the state u prime. Okay. You can easily write an NFA that basically accepts that, right? So take this case. Let's say I have my non-deterministic Büchi automaton A, and I tell you create an NFA, so a non-deterministic finite automaton that accepts all the words V such that running V in A can take us from Q to Q prime. Q and Q prime are states of A. Okay, this is very easy. You just copy A. You say my starting state is Q. My only accepting state is Q prime. Right? And this gives you the NFA that you want. It accepts all the words that go from Q to Q prime. Now, if I say you have to go from Q to Q prime and also see a target vertex, that's also easy. You just keep track of whether you've seen a target vertex or not. You just keep 2 copies of your automaton. 1 copy is for when you haven't seen the target vertices. The other one is for when you have seen. Okay. What if I say create an NFA that accepts all the words such that running V in A cannot take us from Q to Q prime? Again, this is the complement of the previous one, and we know that we can complement NFAs. So for all of these, I can create NFAs for all constraints that are like this. Now, if I have a function f of this format, and let's say f of the state q, let's say, is whatever, q0, q1, and q1. Okay, and let's say that the states that I had were like q0, q1 to q5. What do I know? I know that from state q, I should be able to reach q0, but I have an NFA for that encodes it. From q, I should be able to reach q1. I have an NFA that encodes that. I take those two and I take their intersection. From q, I should not be able to reach q2. So I have an NFA that encodes that. I add that too. I take the intersection of all of those. From q, I have to reach q1, and on the side, on the way, I have to see t. I have an NFA for that. So I just take all of these NFAs that correspond to all of my constraints, and I take the intersection of all of them. And that gives me an NFA. And that NFA accepts exactly the set of words, the set of non-empty finite words that are in this particular equivalence class. So for every equivalence class F, I have a language LF, which is the set of words that basically correspond to this function, and this language is regular. And I know how to find an NFA for it. Okay. Going forward. Here's now where things get interesting. I'm going to make another claim. So you see, I had this definition of equivalence, and I basically broke down my finite words into finitely many equivalence classes. And I showed each one of these equivalence classes by L of some F. Okay. Now, what I claim is this. I say every infinite word W can be decomposed in this format. It can be decomposed such that it has one finite word from some L of F, from one of the equivalence classes, and then it has an infinite number of words, of finite words from another equivalence class. So this means that basically W can be written as V1, V2, V3, so on, such that V1 is in L of F, and all the other ones, V2, V3, and so on, are in L of G. That's the claim. Another way of thinking about this is that I'm saying every infinite word has a prefix, and then after that prefix, it just repeats elements of the same equivalence class. So it has a prefix that is maybe in LF, but then after that, it just keeps repeating elements of some LG. That's my claim. Okay, this is where Ramsey comes in. We have to use this LF and LG and so on. We have to use our equivalence classes as colors in a graph. And that's why it was really important for me to prove that I have finitely many equivalence classes because I wanted to say I have finitely many colors. Okay, so what is the graph that I create? So I say, suppose you give me some infinite word W. Okay, I want to find some finite substrings of W. And I define Wij to basically be the substring from index I to index j minus 1. So it includes I, it doesn't include j. Okay. Now, I create a graph, and I want an infinite graph. So I create a graph where I have one vertex for every natural number in N. And it's also a complete graph. I have an edge between every two vertices. And then when I want to color the edge between vertex I and vertex j, the color that I use is an equivalence class. And I find my equivalence class like this. I first go look at the substring from index I to index j. And then I ask, what is the equivalence class of this substring? Since this substring is finite, it has one of those equivalence classes. Let's say it was in equivalence class LF. Then I color the edge from I to j with that color, with LF. So I'm using my equivalence classes as my colors. Okay, now we apply Ramsey. We have an infinite complete graph, and we've colored the edges with finitely many colors. So this means that there are infinitely many indices, basically. There are infinitely many vertices, let's say, such that all the edges between those vertices are of the same color. Okay? So that means that there are infinitely many indices, I0, I1, I2, so on, such that the substring from I0 to I1, the substring from I1 to I2, and so on, they were all in the same equivalence class. And let's call that equivalence class LG. Okay, great. So I just take the substring from the beginning of my string to I0, and I take its equivalence class, and I call that LF. So now my W is in LF LG omega. Right? Because I could write my W in this way. Basically, I was saying it's from index 1 to I0 plus W from index I0 to I1 plus W from index I1 to I2, and so on. I don't care about this first one, but for all of these other ones, I proved that they are in the same equivalence class, and I called that equivalence class LG. And I just called the equivalence class of this one LF. So W is in LF LG omega. It starts with something in LF, and then it continues with an infinite number of things in LG. Okay. It's just amazing how he came up with this, applying Ramsey theory here to, well, okay. But let's get back to our actual problem. Our problem was that I'm given a non-deterministic Büchi automaton, and I want to complement it. So here's what I say. I say, consider any two of the equivalence classes. Let's call them LF and LG. And let's consider the language of my non-deterministic Büchi automaton A that I wanted to complement. I say that either the language of A does not intersect LF LG omega, or the language of A contains all the strings in LF LG omega. Take all the sets that are of this format, of the format LF LG omega. For each one of these sets, either it's entirely inside the language of A, or it doesn't even touch the language of A. Now, why is that? It's because of our replacement property, right? So if the language of A touches this set, if there is some W that is in this set and it's also in the language of A, Okay, what does that mean? It means that I can decompose W into W1, W2, W3, so on. And W1 is in the language of F, and all of the rest of them are, sorry, W1 is in LF, and all the rest of them are in LG. Okay, but this means that I can replace W1 with anything else that was in LF. And since A accepted W, A will accept the string after that replacement. Similarly, I can replace W2 with everything else in LG. Any other string in LG can be used to replace W2. And it will not change the acceptance, because again, that's how we define our equivalence relation. Okay? So this means that any string that is in LF LG omega is also going to be accepted. So by assuming that only one string in LF LG omega was accepted by A, we could prove that every string in LF LG omega is accepted by A. So this proves the theorem. It proves that either A accepts everything in LF LG omega or nothing in LF LG omega. Okay. Finally, we're getting somewhere. Here are the things that we proved. We proved that there are finitely many equivalence classes LF. So this means that there are finitely many sets of this format, LF LG omega, because if I have n equivalence classes, here I can have at most n squared. Right? Other than that, we proved that every LF is regular. And we also proved that every infinite word is in one of the sets that look like this. And each one of the sets that looks like this either does not intersect the language of my automaton or is completely inside the language of my automaton. So great, I can now create another automaton B. And basically what I do is that I go over all sets of this format. And for every set of this format, since I have finitely many of them, I can go over all of them. For every set of this format, if it's accepted by A, I say I don't put U in B. If it's not accepted by A, I say I put U in B. Now, but of course, when I want to put it in B, I have to be sure that I can create an NBW for this. I can say that my NBWB is just the union of all the NBWs for sets of this format that were not accepted by A. Okay? But why do I have an NBW for this? Well, I know that I have a non-deterministic finite automaton for LF. I have an NFA for LF. And I have an NFA for LG. So I can just combine them to get an NBW for LF LG omega. How can I do that? Well, first, I have to read a word in LF. So I take the NFA of LF and I just say that take every accepting vertex and connect it to the initial vertex of LG. Right? And then for creating LG omega, I do something similar. So I say take the finite automaton that accepted LG and just connect every accepting state back to the initial state. Right? So LG omega means that I want to see words in LG infinitely many times. That's just the same as saying take the finite automaton for LG and connect the accepting states back to initial states, so that when you see a word that is accepted, you can go back and read the next word. Okay, yeah, so I have an MBW for this entire thing. So I have an MBW for each one of the sets that look like this. And for each one of the sets that look like this, I know whether they are in A or not. And if they're not in A, I take their MBW and I take the union of all of these, and that's going to give me the MBW for B. So yeah, the MBWB basically has the language LB, which consists of all those LF LG omegas that are not in the language of A. And again, the important point is that there are finitely many of these. And since there are finitely many of these, I have to just take the union of finitely many automata, and I know that I can take union. So finally, omega regular languages are closed under complementation. If I give you a non-deterministic Büchi automaton, you can create another non-deterministic Büchi automaton that accepts the complement language.